In this video, we're going to look at 2021 Paper 2, Question 8. In the first part of this question, we're told that all the first years in a school did a maths exam. We're told that the average mark was 176. So that's our mu, the average result was 176. We're told the standard deviation is 36, so that's our sigma. And we're told that the top 10% of students go forward to a maths competition, a county maths competition. We need to figure out what mark do you need to get to be in the top 10%. So what's the minimum mark you need to get in order to qualify for this competition? So I've written out, I know what mu is and I know what sigma is. I want you to realize that if we go to our maths tables, we're going to use our standardizing formula here. The formula that ultimately we're going to use is z is equal to x minus mu divided by sigma. Where I know that the sigma is 36, I know that mu is 176. X will be the mark that a student needs to get in order to qualify for the competition. And ultimately that's what I'm trying to find. Based on the fact that I know that you have to be in the top 10% to qualify, that's going to allow me to work out the z. So we need to look at our z scores here. You'll notice here that I've illustrated what's going on. The results are normally distributed, so I've just drawn myself a rough normal curve. And I want to work out what's the minimum mark you need to get so that there's only 10, at the very most 10% above you. Or in other words, that you're in the top 10%. So remember, when we're using our maths tables, those z scores represent the percentage of figures to the left of our value. So if 10% are above it, then obviously that means that 90% are below it. So I want to work out the z score for which 90% of all the figures are below that value. So instead of thinking of it as percentages, we should think of it as 0.9. We should think of this as 0.1. So essentially, what we're doing here is we're using our maths tables in reverse. Look at all of your z scores there, and along the side are the actual z scores, and the numbers in the middle of our table are our probabilities. I want to work out what is the z score for which the probability is 0.9. So we're using the tables in the opposite manner to which we usually use them. We're looking for the closest probability to 0.9. The closest probability you're going to find to 0.9 is 0.8997. That's almost exactly, it's very, very close to the 0.9. And the next one is 0.9015, but it's much further away. So this is the one that we're going to use. If the probability is 0.8997, you should recognize the corresponding z score is 1.28. So if you have a z score of 1.28, then 89.97% of figures are less than whatever your figure is. So that's the z score. In order to identify what the z score of a student who qualifies for this competition is, we just look at our maths tables and that's it. And now we can use our standardizing formula. We know z, we know mu, we know sigma. The only thing we don't know is x. So it's going to be relatively straightforward now to just sub in. Z is 1.28 is equal to x minus 176 divided by 36. And now we just have simple algebra. In order to get rid of our fraction, we're going to multiply both sides by 36. We're going to get 1.28 times 36 is equal to x minus 176. And if we want to get x on its own, we're going to add 176 to both sides. So that would tell me that x is equal to, we'll have 1.28 multiplied by 36, and I'm adding 176 to both sides. Now on the left hand side, if you plug all of that into your calculator, you're going to get 222.08 is equal to x. So that's the number of marks that you need to be in the top 89.97%. It's 222.08. However, we have to be very careful here. We are not going to round this down, we're going to round this up, because we have to make sure that we're in the threshold. We don't want to be a little bit to the left of the threshold we're looking for. We have to make sure that we're definitely in the top 10%, not nearly in the top 10%. So if I round down, then I'm including more than the top 10%. So we actually have to round up, and our answer will be 223 marks. So in this case, in order to qualify for this competition, you need to get 223 marks. We round up because we want to make sure we round into the threshold, so you're in the top 10%, not just slightly below the top 10%. If a student gets 223 marks, they're just slightly above that 10%. Whereas if they get 222 marks, they're just slightly below it. It's a little bit more, there's a little bit more than 10% of students that did better than them. So this is our final answer for part I. In part 2, we're told that a student is awarded a certificate of merit if they get between 165 and 210 marks in the exam. We need to figure out the percentage of students that got the certificate of merit. So I've illustrated this in a little normal curve here. So obviously we're told the average is 176. So students who get 165 are below average. Students who get up to between 176 and 210 are above average. I need to work out the percentage of figures in this normal curve in there. In order to do that, we need to use our standardizing formula twice. For the first one, I'm going to try and get a Z-score for a student who gets 165 marks. In that case, my X is 165, my mu is 176, and my standard deviation is 36. When you plug that into your calculator, you get minus 0.31. Now I've rounded that to 2 decimal places because in a moment we're going to use our maths tables to convert this into a probability, and in the maths tables we can only be so accurate as to 2 decimal places. Then for the other one, instead of using 165, I use 210. 210 minus 167 over 36, and that Z-score works out as 0.94. So these are the extremes. Anyone whose marks correspond to a Z-score between minus 0.31 and plus 0.94 will get a certificate of merit. So now it's a little bit easier. We're going to use our maths tables. We're going to work out the proportion of figures in any normal curve that lie between these two Z-scores. Okay, so we need to work out the proportion of figures within these two Z-scores. There's a load of different ways of doing this, so if you did it differently to me, then that's fine. The way that I've decided to do it is, first of all, I'm getting the proportion of figures to the left of 0.94, so everything to the left of 0.94. And then I work out the proportion of figures to the left of minus 0.31. If I subtract the proportion less than minus 0.31 from the proportion less than 0.94, I'm left with the region in the middle, and that'll give me my final answer. So essentially the probability Z is less than 0.94. I can just read that straight off my maths tables. I get this value. And then there's a little bit more involved getting the probability it's less than a negative Z-score. Remember, instead of less than a negative, that's the same as greater than a positive. So less than minus 0.31 is the same as greater than plus 0.31. And also remember that you can't read the probability Z is greater than a value off your maths tables. Instead, we do 1 minus the probability that Z is less than that value. So this I actually can read from my maths tables. The probability Z is less than this value is 0.6217. 1 minus that gives me 0.3783. So the proportion of figures, or the proportion of students that got less than 165 marks is 0.3783. If I subtract that from the proportion that got less than 210, I'm left with 0.4481. Or in other words, 44.81% of all the first years got this certificate of merit. Okay, in part B, we're told that a newspaper claims the amount of time that students spend studying outside of school each week is 21 hours. So that's our population mean, because the implication is that's all the students in the whole country, all the 6 years in the whole country, the average is 21, so that's our mu. We're told that a survey of 60 students is carried out, so the sample size is 60, and the average works out as 19.8 hours. So the average of the 60 students that was surveyed was 19.8, but the newspaper has claimed that the average is 21 hours. Now, it is possible that perhaps the 60 students that were surveyed just happened to study less than the average student. So just because the average of our sample is different from what the newspaper claimed doesn't necessarily mean that the newspaper's claim is false. Perhaps it just means that the 60 people that were surveyed, the 60 students that were surveyed happened to study a little bit less. We're asked to work out the Z statistic to determine to measure the difference between the 19.8 and the 21. How significant is this difference? Also, we're told the standard deviation is 5.2. You should realize here, we're going to calculate our Z-score in the same manner as we do it when we're doing a hypothesis test. So if you go to your maths tables, to do a Z test, it's X bar, our sample mean, minus mu, which is the population mean, divided by sigma over the square root of n. We can just plug in all of our values here. In this case, 19.8 minus 21 over 5.2 divided by the square root of 60. And if you plug all of this into your calculator, your Z-score or your test statistic works out as minus 1.787. And that's our final answer for B part I. Okay, so in part 2, we're asked to work out the p-value of our Z-score from part 1 and explain what it means in the context of the question. What I want you to realize here is that essentially what we're doing in this question is a hypothesis test. So the hypothesis is we're investigating, is the newspaper's claim true? Could it be true based on the result of our sample? And you know yourself, if you get a Z-score between 1.96 and minus 1.96, then we'd fail to reject the hypothesis. When we were doing hypothesis testing, that's the first way that we made conclusions. And then the second thing that we did was we worked out our p-values. So p-values is simply a different way of concluding after a hypothesis test. So in this case, we weren't asked for a null hypothesis or an alternative hypothesis, but all the maths we're doing is the same. Remember how we get our p-values now. Once we have our Z-score, to work out the p-value, or another word we used to describe a p-value is the critical region. It's the proportion of figures in our normal curve that are more extreme than our Z-score. Our Z-score is minus 1.787. So the p-value refers to the proportion of figures to the left or less than that value. But remember, when we're getting our p-value, it's what we refer to as a two-tailed test. So not only do we want the proportion of figures less than minus 1.787, but also we have to incorporate the proportion of figures greater than plus 1.787. Because everything I've shaded in here on both ends of the spectrum, everything on either end are more extreme than our Z-score, or they're further away from the mean than our Z-score was. So ultimately, in our maths tables, we can only read from 2 decimal places. So rather than thinking of this as 0.787, we just round to 2 decimal places. We are going to solve for 0.79 because that's as accurate as we can be. What I decided to do was to work out this region. Now notice that they're both the same. So if we just work out one region and then multiply by 2, that gives us our p-value. So I decided to take the positive one. I want the probability Z is greater than or equal to 1.79. To read greater than a value from our maths tables, it's the same as 1 minus less than the value. If you work out the probability Z is less than 1.79, it's 0.9633. 1 minus that figure gives me 0.0367. Or in other words, the proportion of figures in here is 0.0367. But then also the proportion of figures here would be 0.0367. We multiply by 2, and our p-value, our answer for our p-value is 0.0734. Remember, when we're making conclusions, if your p-value is bigger than 0.05, then you fail to reject the null hypothesis. If it's less than 0.05, then you reject the null hypothesis. Clearly this value is greater than 0.05, so in this case we're going to fail to reject. Or in other words, the claim that was made by the newspaper, it might be true. There's not enough evidence to suggest that the newspaper were exaggerating. Even though the average of our sample was only 19.8, it's possible that the people that they surveyed for that survey just happened to study less than the average student. So in making our conclusion here, we say, well, look, our p-value is clearly greater than 0.05. That's the critical threshold. If it's greater than 0.05, then we fail to reject. But obviously we have to explain what that means in the context of the question here. And what that means here is there's not enough evidence to suggest the newspaper's claim is false. So it is possible that it's just a coincidence that the result of our sample was 19.8. even though the newspaper claimed it was 21. So that'll get you the full marks for B part II here. In C part I of this question, we're told that we have 23 keys. 12 of them are for classrooms, 6 of them are for science labs, and 5 of them are for offices. We're asked if we select four keys from the 23 keys, what is the probability that the fourth key is the first one that is for one of the offices? So in other words, the first 3 keys that we select are either for classrooms or science labs, and then the fourth one will be for an office. The easiest way to work this one out is, well, we just think, right, how many of them aren't for offices and how many of them are? The number of keys that aren't for offices at the start is 12 and 6, it's 18. So if I randomly select one of those keys, the probability that the first one that I select is not for an office is 18 out of the total of 23. So now we've taken out one of the keys, there's only 22 keys left. So, and there's only 17 keys left that aren't for offices because I've removed one of these. So when I select the second key, the number of keys that aren't for offices is 17 out of a total of 22 keys. Then the next one I select again, and I don't want it to be an office key. There's 2 of them removed now, so there's only 21 keys left. There's 1 less key that's not for an office, so there's only 16 that I could select that aren't for an office. So that's the probability the first 3 of them aren't for an office. But now I want the next one to be for an office. So there's 5 of those keys, and I've removed another key from the total, so there's only 20 left. Then remember, in probability, when you have to multiply and when you have to add, that's often what catches people out. In this case, I want to select a first key and a second one and a third one and a fourth one. And implies that we multiply all of these values by each other. And if you plug this into your calculator, your final answer for the probability that the fourth one is the first office key is 0.1152. In C part 2, we're asked, what's the probability that if we select 3 keys, that each of them is a different type of key, that one of them is a classroom key, one of them is a science lab key, and one of them is an office key. Now, there's problems here. This is far more difficult than part I, because in part I we knew the order in what things were happening. We knew the first 3 weren't for an office and the fourth one was for an office. But here, I don't know, like I could get classroom, then science lab, then office, or I could get office, then classroom, then science lab. Or that's the problem here is that there's a number of different orders in which it could occur. And because of that, as far as I'm concerned, the easiest way to do it is by using this formula. The very, very first thing you would have learned in probability, maybe in second year, is that that probability is simply favourable outcomes over possible outcomes. For example, the probability that you get an even number on a dice is 3 out of 6, because there's 6 possible outcomes and there's 3 favourable outcomes. Now there are a number of different ways of doing this question, so if you do it in a different manner, then that's fine. What I'm going to do here is I have 23 keys and I'm going to select 3 of them. The number of different things that could possibly occur is calculated as I have 23 items and I want to choose 3. 23 choose 3 refers to all the different combinations of 3 keys that I could choose from this key ring. So that's the possible outcomes dealt with. The favourable outcomes is I want to work out the probability that of the 12 classroom keys, I choose one of them. So that's 12, choose 1. That's the number of different ways in which I could choose one of the classroom keys. And I also want to choose one of the science lab keys. There are 6 science lab keys and I want to choose one of them. So it's simply 6, choose 1. And there are 5 office keys, so and means I multiply. There's 5 office keys and I choose one of them. What I have on the top here is the number of favourable outcomes. This represents the probability that the number of ways in which I could choose 1 classroom key, 1 science lab key, and 1 office key. If you just plug this into your calculator, 12 choose 1 by 6 choose 1 by 5 choose 1 divided by 23 choose 1, that gives me your final answer 0.2033. And that'll get you the full marks for part 2.